Welcome to the Agile Software Engineering Deep Dive, the podcast where we unpack the ideas shaping modern software engineering. My name is Alessandro Guida, and I've spent most of my career building and leading software engineering teams across several industries. And today I want to take another small historical detour. Not to talk about the newest AI model, not to talk about yet another framework, platform, cloud service, low-code tool, or miracle productivity booster that promises to remove all complexity from software development. Today I want to go back to something older, quieter, and perhaps almost forgotten. Backus-Naur Form, BNF. For many of us who studied computer science some decades ago, BNF belonged to the world of compilers, formal languages, syntax, parsing, and the famous Dragon Book. It was one of those things you learned when computer science still spent time teaching you how programming languages were defined, not only how they were used. At first sight, BNF may look like a historical curiosity, a notation from the age of compiler courses, parser generators, and serious-looking textbooks. But it is much more relevant than it may seem, because every time we add a formula language, a rule system, a template syntax, a query filter, a workflow condition, a configuration format, or a macro feature to an application, we are doing language design, often without calling it that. And that is where trouble begins. A small language is still a language. It needs syntax. It needs grammar. It needs validation. It needs understandable errors. It needs to evolve without becoming an accidental collection of exceptions, shortcuts, hidden precedence rules, and undocumented behavior. This episode is part one of a short two-part journey into compiler theory. Part one is about BNF, syntax, and why grammar still matters when modern applications become programmable. Part two will look more broadly at compiler thinking itself. LEX, YACC, interpreters, compilers, the Dragon Book, and why this almost forgotten discipline still has something important to teach modern software engineering. This is not nostalgia. It is a reminder that when we allow users to express logic inside our systems, we are no longer only adding features, we are designing languages. And languages need grammar. Let's dive in.
Welcome to the Deep Dive. Today we're actually looking at what you might call a lost foundation of computer science.
Yeah, lost is definitely the right word for it.
Right. And we're pulling this from a really fantastic issue of the Agile Software Engineering newsletter. It's titled Before You Add Macros, Learn BNF.
Which is part one of their series on compiler theory.
Exactly. And our mission today is basically to figure out why those simple little text boxes and search filters in your favorite apps are actually secretly ticking time bombs.
Yeah, time bombs that could totally bring the whole system down.
Right, which, I mean, it sounds super dramatic.
Oh, it sounds incredibly dramatic, but it is a very real and a very expensive problem that is just completely hidden in plain sight.
Yeah, so to understand why, think about a house being built.
Okay, sure.
Usually, you walk by and you admire the things you can actually see.
Yeah.
Like the framing or the layout of the rooms, maybe the nice finish on the kitchen cabinet.
Right, the stuff that's obvious.
Exactly. Nobody really stands on the sidewalk, points at the ground and goes, wow, what a beautifully poured concrete foundation.
Yeah, I've definitely never done that.
Right. But if you skip that concrete and you just start building your walls directly on the dirt, I mean, it doesn't matter how beautiful the house looks.
No, of course not.
Eventually, the dirt just shifts. The structure starts to sink, and the whole thing basically collapses under its own weight.
Yeah, because the foundation, I mean, it's entirely invisible, but it's the single variable that dictates whether the structure is actually going to survive contact with reality.
Exactly.
And, for anyone studying computer science back in the 80s or the 90s, Backus-Naur Form, or BNF, that was literally that concrete foundation.
It was huge.
It was. It was an absolute staple of compiler theory. Like, you learn very early on that a programming language isn't just this loose collection of commands. It actually requires a really rigid mathematical grammar.
But if you look at the landscape today, I mean, that foundation has kind of vanished from the surface, hasn't it?
Oh, completely.
We operate in this era of really slick APIs, cloud platforms, and, those drag and drop low-code environments.
Yeah, the low-code stuff is everywhere.
Right, and everything is just so heavily extracted now that it feels like nobody really needs to think about formal grammar anymore.
Well, we might not think about it, but the need for it certainly hasn't disappeared.
Right.
And because we've sort of lost sight of that foundational discipline, developers and product teams are routinely falling into this massive hidden trap.
Which the author of the newsletter refers to as the trap of the accidental language.
Yes, the accidental language.
Right.
And it's a huge trap.
Let's unpack that a bit.
Yeah.
Because the scenario the article describes is just, well, it's painfully relatable for anyone who has ever built a software product.
Oh, absolutely. It always starts with just one innocent little phrase, right?
It's just a small syntax.
Yes, just a small syntax.
A product owner comes in and they're like, hey, users just want a simple formula field so they can calculate their own local tax rate.
Or, the support team asks for a tiny template feature for automated emails just to swap out a customer's first name, something super basic.
Right. And on day one, it seems totally trivial.
Completely trivial. I mean, you add a little text box.
Yep.
You write a really quick script that looks for, say, a $sign or a bracket, swaps out some text, and you call it a day. It takes maybe an afternoon.
But then reality hits.
Yeah, it always does.
The users get a little taste of that power, and they immediately demand more. So week 2, they're saying, hey, this is great, but can I use a wildcard?
Right. And week 3, they ask, well, what if I want to add a custom variable?
Exactly. And by week 4, it's, can I nest an IF statement inside another IF statement? Oh, and hey, how do I escape a special character if my customer's name actually has a bracket in it?
And before you know it, you're just constantly patching the code.
Right, just Band-Aids everywhere.
Yeah. You add a special condition for one big enterprise customer. You throw in some quirky shortcut for another one.
And then, let's say someone tries to nest a complex wildcard search inside one of those math formulas.
Oh, and your simple little script was definitely not built to handle that level of depth.
No, not at all. So the text parser just gets totally confused, maybe gets caught in an infinite loop, and suddenly your entire application just freezes.
Yeah. Bit by bit, feature by feature, you've accidentally built a sprawling, wildly complex system.
Well, let me just push back on this for a second, putting myself in the shoes of, like, a modern developer.
Okay, sure.
Isn't that just being agile? Like, we're iterating, we're listening to our users, we're getting real-time feedback, and we're just giving them the power they're actively asking for.
Right, it feels like that.
So why is that organic growth so inherently dangerous?
Because when you iterate on syntax without a deliberate plan, you aren't just adding features.
What are you doing then?
You are literally designing a programming language on the fly.
Wow. Okay.
And an undesigned language becomes an unmaintainable nightmare. When a language lacks deliberate architecture, the edge cases just multiply exponentially.
Oh, I can imagine.
Yeah, and the rules become wildly inconsistent.
It's kind of like writing a legal contract without using any punctuation.
Yes, exactly.
You end up with that classic grammar joke, let's eat grandma versus let's eat grandma.
Right, the comma saves lives.
It really does. Because if the user doesn't have a strict, predictable grammar to follow, the system might misinterpret the command entirely and will actually end up eating grandma.
That is a perfect analogy. Without the comma, without that formal structure, the meaning shifts entirely.
Right.
And in software, this manifests as silent failures. Or you get those completely cryptic error messages.
Oh, I hate those.
Right. Have you ever used a search filter in a database where you try to combine an AND with an OR and the system just throws up a blank screen?
Yes. All the time. Or you look at the documentation, and instead of clear rules, it's just this messy list of 10 hyper-specific examples.
Oh, yeah, and you just have to blindly guess how to combine them.
I have absolutely been there. You end up just copying and pasting their exact example because you know that if you change even a single parenthesis, the whole thing just catches fire.
Exactly. And that fragility happens because syntax is not just user documentation. It is a fundamental engineering decision.
Okay, that's a key point right there.
Yeah. Creating small domain-specific languages is incredibly useful, don't get me wrong.
Sure.
But an undesigned small language means the developers themselves will eventually be terrified to touch their own code.
Because they have no idea what's going to break.
Precisely. They have no idea what undocumented edge cases their users are relying on.
So if building these tiny features organically is what ultimately causes the collapse, how do we force ourselves to be more deliberate? How do we pour the concrete, so to speak.
By treating syntax as math.
Math, okay.
Which is exactly what Backus-Naur Form, or BNF, was originally invented to do. It is the historical antidote to the accidental language.
And the newsletter has a really brilliant section where it demonstrates this, right?
Yeah.
It builds a tiny calculator language from scratch using BNF.
Yeah, just a feature that lets a system add and multiply numbers.
Now, we are deliberately not going to read the actual BNF code to you on this deep dive.
No, please don't.
Yeah, because reading lines of recursive brackets, pipes, and hierarchical terms out loud would basically sound like we're reciting robot poetry.
Robot poetry is honestly the best way to describe it. Audibly, it's totally impenetrable.
Right, but visually it is fascinating.
It really is.
And I strongly urge you, the listener, to pull up the written article in the Agile Software Engineering newsletter to actually see these examples for yourself.
Yes, definitely that.
Because seeing the syntax visually map out the logic,
Yeah.
it makes the entire concept click instantly.
Oh, absolutely.
And when you look at it, it's actually kind of funny.
How so?
Well, it just looks wildly overcomplicated at first glance. It's this rigid, academic, multi-layered notation just to define what a number is or what a simple plus sign does.
Right.
You look at it and you think, why on earth am I writing 5 lines of formal recursive logic just to teach a computer what 2 plus 3 means?
It does feel like massive overkill, at least until you hit the core aha moment of compiler theory.
Okay, lay it on me.
Let's consider a slightly longer math equation, say 2 plus 3 times 4.
Simple enough? 2 plus 3, 4.
Right. Now, if you solve that on paper, what is your actual process?
Well, I multiply the 3 and the 4 first to get 12, and then I add the 2, so the answer is 14.
Exactly. And you do that because human beings intuitively learn the order of operations in grade school.
Right, PEMDAS or whatever.
Yeah. We just know that multiplication has a higher precedence than addition,
Sure.
but a computer does not know that.
Really? It doesn't just know math.
No. A computer just sees a flat string of text characters. If it reads naively from left to right, it adds 2 and 3 to get 5, multiplies that by 4, and spits out 20.
Which is completely wrong.
Exactly. So how does BNF actually solve that order of operations problem without the developer just having to write an endless, messy string of if-then statements?
By using structural depth to enforce the rules.
Okay, what does that mean?
In that quirky robot poetry of BNF, you don't just list symbols in a row. You define a strict hierarchy.
A hierarchy.
Yeah, you separate the concept of a term, which are the elements being multiplied from a factor. By placing the rules for multiplication lower down, deeper in the grammar tree, you literally force it to bind more tightly.
Oh, wow.
Yeah, you are explicitly teaching the computer precedence simply by the physical shape of the rules.
Oh, that makes so much sense. You are entirely removing the ambiguity before the computer even attempts to run the math.
Yes. You're forcing the system to stop treating the input as raw text. Instead, it converts that text into a structured logical tree.
Right.
It knows exactly what is allowed, what takes priority, and exactly where every single piece belongs. That's brilliant. And looking at the modern landscape, the newsletter makes a really bold claim about why this matters more today than ever before.
It does.
It points out that the boundary between users and programmers is rapidly vanishing.
And you really see that if you think about the software we interact with daily now.
Yeah, AI is everywhere.
Exactly. When a marketing manager writes a highly structured AI prompt where they define variables, they set negative constraints, they dictate an expected JSON output format, what are they actually doing?
I mean, they're programming.
Exactly.
They wouldn't put it on their resume as software engineering, but structurally, that is programming.
And exactly the same thing happens when an HR director sets up a complex workflow condition in a CRM, or when someone builds an automated rule for a ticketing system.
Right.
We are giving millions of everyday users access to these small, highly specialized languages.
And if we are going to hand everyday users the power to program our platforms, we owe them a predictable grammar.
We owe them clarity and we owe them safety. If a user makes a structural mistake in their workflow rule, they shouldn't just get a silent failure that slowly corrupts their entire database.
That would be a disaster.
They need a system that understands its own grammar well enough to immediately flag it and say, hey, you opened a parenthesis right here, but you never closed it.
So does that mean every web developer and product manager out there needs to just drop what they're doing and go back to school to become a compiler engineer?
No, not at all. And the source is actually very clear about easing that exact anxiety.
Phew. Good.
You do not need to write native machine code generators. You don't need to build complex memory optimizers.
Okay, so what's the actual goal then?
The goal is simply to adopt the compiler theory mindset.
Ah, the mindset. So it's about the philosophy of how you handle user input.
Exactly.
Like, instead of a bouncer at a club, just quickly glancing to see if you have a piece of paper that kind of looks like a ticket.
Right.
It's more like the bouncer checking. If the ticket is for the right day, the right seat, and actually valid for this specific venue before letting you anywhere near the door.
That is a brilliant way to frame it. The compiler mindset essentially means separating your syntax from your meaning.
Separating syntax from meaning.
Yeah. You parse the input before you ever try to execute it.
Let's break down that mechanism a bit. What does parsing actually look like under the hood?
So it happens in distinct stages. First is lexing.
Lexing.
Yeah, that's where the system reads the raw text and chops it up into meaningful tokens. So 2 plus 3 becomes a number token, a math operator token, and then another number token.
Got it.
Then comes parsing,
Right, step 2.
where the system takes those tokens and builds that hierarchical tree we talked about earlier, what we call an abstract syntax tree, or an AST.
AST, right?
Yes. And you validate everything structurally before a single action is actually taken.
So you're designing for extension from day one.
Exactly. So when users ask for those inevitable new features we talked about, your language can actually scale without just collapsing in on itself.
Okay, so if I'm a developer listening to this right now, and I suddenly have this cold sweat, realizing I've accidentally built a sprawling, unmaintainable language in our app's search bar.
Which happens to the best of us.
Right, but where do I turn? Like, what is the roadmap out of the accidental language trap?
Well, the newsletter actually provides a really phenomenal library of language design.
Oh, nice.
Yeah, it lists 5 foundational texts that chart the whole journey, from abstract theory all the way down to modern practical application.
Let's trace that journey then. Where does the theory begin?
It starts with a real historical document, the Agile 60 report.
Ah, Agile Vixie by Peter Noer. Yeah.
Yes, by Peter Nur and others. And alongside that is John Backus's paper on algebraic language.
Okay.
These 2 works basically represent the genesis of formal structure, because before this, programming languages were mostly defined by writing out these long-winded prose descriptions and just providing a few examples.
Oh, wow. That sounds messy.
It was. But these documents brought actual mathematical engineering precision to syntax. They proved you could systematically define a language rather than just describing it.
It's the moment the industry basically stopped eyeballing the blueprints and finally started using a ruler.
Exactly.
But how did that raw math translate into the complex systems we use today?
So that bridge is the legendary text called compilers, principles, techniques, and tools.
Oh, the Dragon Book.
Yes, universally known as the Dragon Book because of the literal dragon on the cover.
Right.
It is the symbolic heavyweight of compiler theory. It takes the formal grammar from Backus-Naur and places it into the full pipeline.
The pipeline from text to execution.
Right. It explains the entire mechanism of taking raw source text, running it through the lexer and the parser, building the abstract syntax tree, extracting the meaning, and then finally executing it safely.
Okay, so that covers the grand theory and the full pipeline.
Yeah.
But what about the practical side? Like, if I need to actually write the software that reads this grammar, what's my toolkit?
For the actual mechanics of reading grammar, you turn to parsing techniques by Dick Gruen and Cyril Jacobs.
Parsing techniques.
Yeah. If BNF is the map, parsing is the vehicle. This book tackles the incredibly complex challenge of writing software that can recognize and structure really messy human input.
Messy human input is definitely the hardest part.
Without a doubt. And finally, for the modern developer, the person building domain-specific tools, complex configuration readers, or workflow engines.
Right, the stuff we build today.
Exactly. The ultimate modern playbook for that is Language Implementation Patterns by Terence Parr.
Ah, I've heard of that one. That's the text that skips the deep abstract theory of machine code generation and just focuses straight on the programmable layers we add to everyday apps.
Precisely. It gives you the actual patterns to safely build rules, filters, templates, and formulas for your users without creating a total maintenance nightmare.
You know, what really stands out about this journey is the unbroken lineage of it all.
Yeah, it's pretty remarkable.
Because even if a developer today isn't using raw BNF, maybe they're using JSON schemas to strictly format their data payloads, or PEG grammars for modern parsing.
Or even just writing highly complex regular expressions to find patterns in text.
Exactly. They are still standing squarely on that same concrete foundation.
Absolutely.
They're utilizing tools that were built on the fundamental premise that a formal definition is infinitely better than just a vague intention.
Well said. The notation we use day to day might evolve, but that core engineering discipline remains completely untouched.
So, to summarize the core lesson from today's deep dive, whenever you allow your users to express complex logic inside your application, you are no longer just designing a feature.
No, you are not.
You are designing a language.
And languages need grammar.
They need grammar. Because if you fail to define that grammar up front, the language is just going to define itself organically.
Yeah, through a really messy web of accidents, edge cases, and incredibly frustrated support tickets. And I'd actually love to leave you with a final thought to mull over.
Let's hear it.
The next time a user complains about a quote-unquote bug in your application's search filter or a workflow tool starts behaving unpredictably, ask yourself, is the code actually broken? Or is the invisible language you accidentally created just speaking a dialect that even you don't fully understand?
Oh, wow. That is a phenomenal question to end on. If you want to stop building on dirt and start pouring a solid concrete foundation for your own projects, you really need to subscribe to the Agile Software Engineering newsletter where this deep dive originated.
Highly recommend it.
Seriously, go subscribe right now so you don't miss part 2 of this series on compiler theory.
Yeah.
And make sure you are subscribed to this podcast as well.
Yes, definitely.
But most importantly, share this deep dive and the Agile Software Engineering newsletter with your network. You know, your team, your product managers, your developer friends.
Sharing is the best way to spread the knowledge.
It absolutely is the best way to spread the knowledge of Agile software engineering and stop the plague of accidental languages. Thanks for exploring the foundations with us today, and we'll catch you next time.
Thank you for listening to the Agile Engineering Deep Dive podcast. If you found this episode valuable, feel free to share it with someone who might benefit, a colleague, your team, or your network. You can access all episodes by subscribing to the podcast and find their written counterparts in the Agile Software Engineering newsletter on LinkedIn. And if you have thoughts, ideas, or stories from your own engineering journey, I'd love to hear from you. Your input helps shape what we explore next. Thanks again for tuning in, and see you in the next episode.